Welcome everyone to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. I'm excited about today's topic. It's something that has been gaining traction in the scientific community, and it's all about pushing the boundaries of AI.
Absolutely. Today, we're diving into this article entitled, "Is Your Agent Smarter Than a Fifth Grader?" It raises a really interesting question. How do we actually measure and define intelligence in machines? And how far away are we really from achieving something comparable to human-level understanding?
It's a provocative title, that's for sure, but it hints at a much deeper issue, right? Are we focusing on the right benchmarks? Are standardized tests, even ones designed for kids, really capturing what we mean by intelligence when we talk about AI?
Exactly. And it begs the question of what benchmarks we should be using. Just passing a test doesn't mean it understands the underlying concepts. It could just be really good at pattern matching, which current deep learning is really good at.
That's a great point. I think what's interesting here is the implicit assumption that human intelligence, as measured by these tests, is the gold standard, which, it is a standard, but is it necessarily the standard we should be aiming for?
Well, I think the point is to see how well an AI can do on tasks that require a broad understanding of different subjects, which is what these standardized tests are supposedly measuring. If an AI can't even perform at a fifth grade level, then it raises concerns about its ability to truly reason and generalize.
But isn't that assuming that the way a fifth grader reasons and understands is the optimal way? I mean, we're constantly refining our educational methods because we realize kids don't always learn and reason in the most efficient way. Maybe AI can find better routes to solutions, even if they don't mimic human thought processes.
I'm with you there. Fifth grade tests are designed to assess a very specific set of skills learned through a specific curriculum. It's not necessarily a measure of inherent intelligence, more a measure of how well someone has absorbed information and can apply it in a specific context. You could probably teach an AI to ace these tests through rote memorization without it having any actual understanding.
Yes, and that's the critical distinction, isn't it? The difference between performance and understanding. We've seen AI systems excel at games like Go and chess, but does that mean they understand the game in the same way a human grandmaster does? Or are they just exploiting patterns and probabilities?
Okay, but let's not downplay the achievements of those AI systems. I mean, AlphaGo's ability to make moves that were initially considered unorthodox by human experts showed that it was capable of going beyond pre-programmed strategies and actually innovating. Isn't that a form of understanding, even if it's different from human understanding?
I think the innovation you are talking about is really just the result of the brute force approach. They are going through millions of possibilities that a human can't do and finding the best strategy. It doesn't mean they understand anything about the game. I still maintain that these systems lack genuine understanding. They can identify patterns and correlations, but they don't grasp the underlying causal relationships or the abstract concepts that humans use to reason about the world.
Yes, and that lack of understanding becomes really apparent when you try to apply these AI systems to real-world problems that are less structured and more ambiguous than a game of Go. If you've trained on a specific board game, you are not learning how to play checkers or chess. The agent has to be retrained.
Right, the issue of generalization. If an AI system can only perform well on the specific tasks it was trained on, it's not truly intelligent. True intelligence requires the ability to adapt to new situations, to learn from limited data, and to transfer knowledge from one domain to another. I think one of the key questions is, how do we build AI systems that are capable of this kind of flexible and adaptable learning? The brain is really good at doing this by learning from very limited data. Why aren't we researching this aspect more?
Well, that's where things like transfer learning come in, right? The idea of pre-training a model on a massive data set and then fine-tuning it for a specific task. We're seeing some success with that, especially in natural language processing with models like GPT-3 and beyond. I think the new models coming out have surpassed the limitations we were talking about.
But even with transfer learning, the AI is still relying on patterns and correlations learned from the initial dataset. It's not truly understanding the underlying principles that govern the new test. It's more like adapting an existing template rather than constructing a new understanding from scratch. To really achieve human-level intelligence, we need AI systems that can reason abstractly and make inferences based on causal relationships, not just statistical associations.
And to build on that, current deep learning models struggle with situations that require reasoning about space and time. For example, predicting how a series of actions will affect the environment or understanding the consequences of past events. These models just lack the ability to represent and manipulate information across different spatiotemporal frames. and these frames of reference should be translatable between each other.
Yeah, I agree. The lack of spatiotemporal reasoning is a major limitation. I've been doing some work on neural pathways involved in decision-making in primates, and it's striking how intricately these regions handle information about time and space. It's not just about recognizing patterns, it's about understanding how those patterns evolve over time and how they relate to the agent's position and actions in the world. How can we reverse engineer these algorithms and implement them into AI?
That's fascinating. So, you're suggesting that by studying the brain's mechanisms for spatiotemporal reasoning, we can develop more effective AI algorithms. I mean, that makes sense. But how do we actually translate those biological insights into concrete computational models?
Exactly. And how do we integrate those models with symbolic reasoning? I still believe that neurosymbolic AI is the most promising path forward. We need systems that can combine the pattern recognition capabilities of neural networks with the logical reasoning abilities of symbolic systems. This would allow AI to not only recognize patterns, but also to understand the underlying causes and effects, which is crucial for true intelligence.
I think you're both on something there. Integrating neuroscience, symbolic reasoning, and spatiotemporal understanding seems like a powerful combination. But it's also a huge challenge. How do we bridge the gap between the continuous, analog signals of the brain and the discrete, symbolic representations of logic?
That's the million-dollar question, isn't it? I think one approach is to focus on developing more biologically plausible neural networks. Networks that are not just inspired by the brain, but actually mimic its structure and function. For example, we could incorporate spiking neural networks, which more closely resemble the way neurons communicate in the brain. Or we could use recurrent neural networks to model the temporal dynamics of neural activity.
Yeah, and I think there's a lot of potential in exploring different architectures beyond the standard feed-forward networks. Things like attention mechanisms, which allow the AI to focus on the most relevant parts of the input, and transformers, which have revolutionized natural language processing. These architectures are showing promising results in capturing long-range dependencies and contextual relationships, which are essential for reasoning and understanding.
But we also need to move beyond purely data-driven approaches. I'm concerned that the current obsession with massive datasets is blinding us to the importance of knowledge representation and reasoning. We need to develop AI systems that can explicitly represent knowledge in a structured way, using things like ontologies and knowledge graphs. This would allow them to reason about the world in a more principled and explainable way, rather than just relying on statistical correlations.
Yes, and to build on that, we need to find better ways to represent space and time in AI systems. I've been experimenting with different coordinate systems and transformation algorithms, and it's clear that this is a major bottleneck. Current AI systems struggle to generalize to new situations because they lack a fundamental understanding of how objects move and interact in space and time. We need to develop AI systems that can reason about these relationships in a more intuitive and flexible way.
So, it sounds like we're all converging on the idea that achieving true AI requires a more holistic approach, one that integrates insights from neuroscience, symbolic reasoning, and spatiotemporal understanding. But how do we actually put this into practice? What are some concrete research directions that we should be pursuing?
Well, from my perspective, I think we need to continue scaling up our deep learning models and exploring new architectures. The sheer size of these models is allowing them to capture increasingly complex patterns and relationships in the data. I also think we need to focus on developing more efficient training algorithms and hardware, so that we can train even larger models without consuming excessive amounts of energy. I believe that scaling is the only way.
I disagree. I think the focus on scaling is misguided. We need to shift our attention to developing more principled and knowledge-based AI systems. I think we should be investing more in neurosymbolic AI, exploring how to integrate symbolic reasoning with neural networks. We also need to develop better ways to represent knowledge in AI systems using things like ontologies and knowledge graphs. In my opinion, this is a more promising path towards true intelligence.
I'm with Sarah on this one. I think we need a more fundamental shift in how we design AI algorithms. I think we should be focusing on developing AI systems that can reason about space and time in a more intuitive and flexible way. I'd like to see more research into coordinate transformation algorithms and spatiotemporal reasoning models. I think this is the key to unlocking true intelligence.
And from my perspective, I think we need to delve deeper into the brain's mechanisms for learning and reasoning. I'd like to see more research on biologically plausible neural networks, spiking neural networks, and recurrent neural networks. I'm also interested in exploring how we can use brain-computer interfaces to create more natural and intuitive interactions between humans and AI systems. Learning how the brain operates may prove to be our best strategy for achieving true AI.
But aren't we in danger of getting bogged down in the details of the brain? I mean, the brain is incredibly complex, and we still don't fully understand how it works. Maybe we should focus on developing simpler, more abstract models of intelligence rather than trying to replicate the brain's complexity exactly. Can we truly understand the elegance of the brain?
I think there's a middle ground. We don't need to replicate the brain exactly, but we can learn from its principles. The brain provides a proof of concept that intelligence is possible, and it offers valuable insights into how to achieve it. For example, the brain's hierarchical organization and its ability to represent knowledge in a structured way are lessons that we can apply to AI design.
Yes, and the brain's ability to seamlessly integrate information from different sensory modalities and to reason about space and time is another key lesson. We need to develop AI systems that can mimic these capabilities if we want to achieve true intelligence.
Exactly. And I think that by combining insights from neuroscience, symbolic reasoning, and spatiotemporal understanding, we can create AI systems that are not only intelligent but also robust, adaptable, and explainable. Systems that can truly understand the world and interact with it in a meaningful way. This is not only a fascinating scientific challenge, but it also has the potential to transform our lives in countless ways.
Well, I'm still betting on scaling and deep learning. I think that in the next few years, we're going to see even more impressive breakthroughs in AI and that we're getting closer and closer to achieving AGI. If AGI can be achieved and what it means for mankind remains to be seen.
I remain skeptical, but I'm also hopeful that we can find a more principled and knowledge-based approach to AI. I think that neurosymbolic AI is the key, and that we'll see significant progress in this area in the coming years.
And I'm convinced that spatiotemporal reasoning is the missing ingredient in current AI systems. I'm excited to see what the future holds for this field, and I believe that we're on the cusp of a major breakthrough.
Me too. The potential for AI to revolutionize our world is enormous, and I'm excited to be a part of this journey. This concludes our conversation today about Is Your Agent Smarter Than a Fifth Grader? We hope our listeners found it both insightful and thought-provoking. Until next time on Cognitive Spirals.